Welcome back, everyone, to the deep dive. This is our fourth time, believe it or not, exploring these fascinating quantum computing review articles.
It's great to be back.
Yeah. So today, we've got a really interesting one you shared from the International Journal of Mathematical Sciences and Computing. It came out October 2022.
That's the one. Gives a pretty solid overview.
So our mission really for the next half hour or so is to unpack this article for you. We want to pull out the core insights, where quantum computing stands now, the basic ideas behind it, and importantly, the big hurdles it's still facing.
Think of it as your essential briefing based on this review.
Exactly. So the article kicks off with something I found quite striking. It talks about how we're shrinking computer chips down, getting close to what, 10 nanometers?
Right, around that scale. And at that point, things get weird, or rather, quantum.
Meaning classical physics doesn't quite cover it anymore. For electrons, I mean.
Precisely. Their quantum nature just takes over. You can't ignore it. So the review points out we're kind of at a fork in the road.
Okay. What are the options?
Well, path one is trying to engineer around these quantum effects. Stick with classical design somehow.
Uh-huh. Seems tricky.
Or path two, embrace it. Actually use those quantum properties. And that fundamentally is the driving force behind quantum computing research.
Right. Harnessing the quantum weirdness instead of fighting it. The review goes into some history too, doesn't it? Feynman.
It does. Yeah, back in the 80s, Richard Feynman had this brilliant idea. He said, look, if you want to simulate a quantum system, what better tool than a computer that runs on quantum mechanics?
That just seems so elegant, so logical. Use the system to model itself.
Exactly. It kind of lit the fuse. And then fast forward to 1994, Peter Shor comes along.
Ah, Shor's algorithm. That's the famous one, right? For prime factorization.
The very one. And it wasn't just, a neat theoretical trick. It showed that quantum computers could potentially break the encryption that secures, well, a huge amount of our digital world.
Because factoring large numbers is super hard for normal computers, but Shor's algorithm makes it easier for a quantum computer.
Exponentially easier, in theory. That's the key. Classical computers take potentially billions of years for really big numbers. A quantum computer, maybe hours or days. That's the potential threat to things like RSA encryption.
Wow. Okay, so that really puts the pressure on developing quantum-resistant cryptography too, I imagine.
Absolutely. It's a huge driver. The review also mentions another key early algorithm, Grovers?
Grovers, that's for searching, isn't it?
Yeah, searching unstructured databases. It doesn't give that same exponential leap as Shor, but it offers a quadratic speedup, still significantly faster than classical methods for finding that needle in a haystack.
So we have these specific but really powerful potential speedups. The article then brings up something else interesting. Zero energy dissipation.
Ah, yes. This is a fascinating theoretical point.
Yeah.
See, classical computer gates, when they operate, they're irreversible. They lose information, and that generates heat.
Okay, like erasing something.
Right. But quantum operations, the gates, they have to be unitary, which means they're reversible. In principle, you can run a quantum computation and then run it backwards perfectly.
And that means no heat generated. Theoretically.
Theoretically, yes.
Mm-hmm.
It could potentially bypass fundamental limits on energy efficiency in computing. Now, the review is careful to say in theory.
Because actually building it is another story.
Exactly. Practical systems still have losses, decoherence, which we'll get to, but the potential for ultra-low energy computing is there. And the review notes, just like classical computing, builds complexity from simple gates.
Quantum computing does the same with quantum gates.
Right. Complex calculations can be built up from basic single-qubit and multi-qubit gates.
Okay, so that brings us nicely to the current state of play. The review says we're still early days, right? No supercomputer beating quantum machine just yet.
Definitely early stages. But there are real systems being built and tested. The review highlights IBM Q, for example.
IBM's cloud platform.
Yeah. They provide access to processors with 5, 16, 20 superconducting qubits, and these things run incredibly cold.
How cold?
Like 15 millikelvin.
Yeah.
Colder than outer space.
Wow. Just to keep the quantum state stable?
To minimize noise, yeah.
Yeah.
Shows how sensitive they are. Then there's D-Wave.
So there's a different approach, right? Quantum annealing.
That's right. The D-Wave 2000Q mentioned uses annealing, which is geared towards optimization problems, sampling, some machine learning tasks. It's not the universal gate model like IBM's.
And big names are actually using these.
Yeah.
Lockheed Martin, Google, NASA.
Yeah, for specific complex problems where annealing might offer an advantage, it shows there are different paths being explored.
And the review also mentions Intel and Microsoft are investing heavily.
Which is a huge signal, right? These tech giants see long-term potential here, not just, academic curiosity.
Definitely. Okay, so let's get down to the nitty-gritty. Qubits. How does the review explain the difference from classical bits?
Well, the core ID is superposition. A classical bit is stuck,
Hmm.
either 0 or 1. Definite. A qubit, though, can be in a superposition. It can represent both 0 and 1 at the same time, with certain probabilities.
So when you do something to the qubit,
You're kind of doing it to both the 0 and 1 possibilities simultaneously.
that sounds efficient. Is that quantum parallelism?
That's exactly it. If you have n qubits, they can represent 2 to the power of n states all at once. Operate on that system, and you're effectively operating on all those 2n values concurrently.
Which gives you that potential exponential speedup we talked about.
Precisely. That's the source of the power.
The review shows the math for a single qubit, a CO trime plus MAA. What do alpha and beta mean again?
They're complex numbers called probability amplitudes. If you square their magnitude A2 and A2, you get the probability of measuring the qubit as 0 or 1, respectively.
And those probabilities have to add up to 1.
Always. A2 plus 0, 1 when you measure.
Okay. And with more qubits, say k qubits, you get 2k basis states. The review mentions Hilbert spaces here. That sounds important, but maybe a bit abstract.
It's the mathematical framework, yeah. Think of it as the abstract space where all possible quantum states live. It's a vector space, but with extra rules for quantum mechanics.
So each possible configuration of the qubits is a point or a vector in this Hilbert space.
Kind of, yeah.
Yeah.
And the math of Hilbert spaces, vector addition, multiplication, inner products, gives us the tools to describe how these states evolve and interact.
Got it. And when you combine multiple qubits, the review talks about the tensor product, using that little symbol.
Right. The tensor product is how you mathematically combine the state descriptions of individual qubits to get the state description of the whole system, the whole register.
So if you have two qubits, each in its own superposition.
The tensor product gives you the combined state, which includes terms for all 4 possibilities. 0, 0, 1, 0, 1 error, 10 error round, each with its own probability amplitude derived from the original alphas and betas.
Okay, so it scales up the complexity and the possibilities. The review goes back to superposition then. Using an analogy, I liked a particle taking multiple paths at once.
Yeah, that wave-particle duality. A quantum particle can behave like a wave, exploring multiple possibilities simultaneously. Superposition is the qubit equivalent. It's not just 0 or 1, it's a weighted combination of 0 and 1.
And for two qubits, it's a combination of 00 R 0, 1 arrow A 11.
Exactly. And as you add qubits, the number of possibilities in that superposition grows exponentially. That's the engine.
Now, you can't talk quantum without mentioning entanglement. The review calls it an instantaneous interaction, even over large distances.
It's definitely one of the weirdest but coolest aspects. Entangled particles are linked. Measure one, and you instantly know something about the other no matter how far apart they are.
Like they're communicating, but they're not.
There's no communication faster than light, but their fates are correlated in a way that classical physics just can't explain. It's a statistical correlation established when they were entangled.
And this isn't just weird, it's useful. The review mentions algorithms and secure communication.
Hugely useful. It's a resource. Many quantum algorithms rely on entanglement to work. And in quantum communication, if someone tries to eavesdrop on entangled particles, it disturbs the entanglement, revealing the eavesdropper.
But it's hard to create and maintain, especially with atoms.
Oh, absolutely. It's incredibly delicate. You need precise control and isolation from noise. That's a major engineering challenge. But those correlations it enables are a key advantage.
Okay, circling back quickly to quantum parallelism, the review stresses again how superposition lets you do many calculations at once. And that factoring example comes up again.
Yeah, factoring a 500-digit number classically might take billions of years. Quantumly, maybe a year. It's just a different scale of computation for that specific task.
Mind-boggling. So how do we actually do these computations? Quantum circuits and gates. Is it like classical circuits?
There are analogies. A quantum circuit is a sequence of operations, quantum gates applied to qubits. Then usually at the end, you measure the qubits to get the answer.
But the gates themselves are different. They have to be unitary.
Yes, unitary means reversible, as we discussed. No information loss. This allows for a much wider range of operations than simple classical and or not gates.
The review lists some basic single qubit gates, poly T, XYZ, phase S, and the Hadamard H.
Right. I as identity does nothing. X is like a classical not T. It flips 0 year to 1R and 1 to 0 year.
Okay.
Y and Z also act on the state but introduce phase shifts, which are crucial in quantum algorithms. S is a specific phase shift gate.
And the Hadamard, the review calls it crucial.
It really is. The Hadamard H gate is your go-to for creating superpositions. It takes a simple 0 state and turns it into an equal mix of 0 air and 1 air. Except for 1 air, it turns it into a different equal superposition. Absolutely fundamental.
So that's how you get the qubits into that both states at once mode to start things off.
Often, yes. It's key for initializing many algorithms.
Then there are multi-qubit gates. The CNOT, controlled not. That sounds like interaction.
Exactly. CNOT takes 2 qubits, a control and a target. If the control qubit is 1, it flips the target qubit. If the control is 0, it does nothing to the target.
Ah, so one qubit state controls an operation on another. That's how you create entanglement.
It's one of the primary ways, yes. That conditional logic is essential. The review also mentions things like NOT2, which is just applying a not T gate to the second qubit in a pair, for example.
So you string these single and multi-qubit gates together like programming steps to run an algorithm.
Pretty much. That sequence forms the quantum circuit.
And we come back to reversibility. All these unitary gates are reversible. The review links this to Landauer's principle, again, overcoming heat limits.
Right. Landauer says erasing information costs energy, creates heat. Since quantum gates don't inherently erase information, they're reversible, they could potentially compute with far less energy dissipation.
Again, that theoretical potential is huge. The review even shows how 2 Hadamards in a row cancel each other out, illustrating that reversibility.
It's a neat example, yeah. H applied twice gets you back restarted.
Okay, but it's not all smooth sailing. The review wraps up by focusing on the challenges, and it sounds like there are some big ones.
Oh, definitely. Building the machines themselves is challenge number 1.
What's so hard?
Well, first, there's no single agreed upon blueprint, no standard way to build qubits yet. And they are incredibly sensitive to everything: vibrations, stray magnetic fields, temperature fluctuations. Any tiny bit of noise can ruin the calculation.
Keeping that quantum state pure is the hard part.
Extremely hard. You need amazing isolation. The review mentions techniques like ion traps, quantum dots, NMR, cavity QED. Always researchers are trying to shield the qubits.
And just making the qubits is tough too. Different approaches like using particle spin or photon polarization.
Yes, and each method has pros and cons. How easy is it to initialize them, to control them with gates, to measure them reliably? And crucially, how long do they stay quantum before decoherence kicks in?
Decoherence, that seems to be the big villain in this story. The review really highlights it.
It's arguably the biggest bottleneck right now. Decoherence is when the qubit loses its quantumness, its superposition and entanglement, because it interacts with the environment. The information leaks out, the computation fails.
So even if you have a great algorithm and perfect gates, if your qubits decohere too quickly,
You can't run the computation long enough to get a useful answer. Improving coherence times is a massive area of research across all qubit types. The superconducting ones IBM uses, the topological ones Microsoft is exploring, D-Wave's annealing approach, everyone's fighting decoherence.
it sounds like a race against time almost for every computation.
In a way, yes. You need to compute faster than the system decoheres.
And finally, the review mentions measurement itself as a challenge, because looking at a quantum system changes it.
That's another fundamental quantum rule. You can't just peek at a qubit state without potentially collapsing its superposition. Measuring forces it into a definite 0 or 1. So extracting the answer isn't always straightforward, especially if the answer lies in the probabilities themselves.
So pulling it all together, the theory is amazing, revolutionary even. But the practical side, building stable, scalable, error-resistant machines, still has a long way to go.
That sums it up pretty well. This review gives a really good snapshot, I think. You get the core ideas: qubits, superposition, entanglement, parallelism, the basic gates, and a clear sense of the major hurdles ahead, especially decoherence and scaling.
Yeah, this has been incredibly helpful for wrapping my head around it all. For me, just understanding the sheer fragility of it all and the ingenuity needed to even get these basic systems working is amazing.
It really is cutting edge science and engineering colliding. The progress is rapid, but the mountains left to climb are still pretty high.
Absolutely. So, for everyone listening, what parts of this deep dive really caught your attention? Was it the algorithms, the hardware challenges, maybe the encryption implications?
We'd love to know.
Yeah, definitely let us know in the comments if there are specific review articles, maybe on quantum error correction or different hardware platforms or specific algorithms that you'd like us to tackle in a future deep dive. Please suggest them.
Your feedback really helps us figure out what to focus on next.
It really does. And of course, if you found this useful and want more deep dives into cutting edge research like this, please do subscribe to the channel here on YouTube.
We appreciate the support.
We certainly do. Thanks for joining us, and we'll see you on the next deep dive.